Determining the appropriate branch circuit size for rack-mounted IT equipment involves more than simply adding up the nameplate ratings. The National Electrical Code, or NEC, provides guidelines that allow for a more realistic assessment of the actual load. This approach considers the running load and takes into account diversity factors, which can reduce the overall calculated load when multiple devices are unlikely to operate at their maximum ratings simultaneously. Here's a detailed procedure for calculating the branch circuit size, illustrated with an example. The first step is determining the running load. It's crucial to measure or estimate the actual running load of each piece of equipment. This can be done using a clamp-on meter or another suitable measuring device. Unlike nameplate ratings, which represent the maximum possible draw, the running load reflects the typical power consumption during operation. The second step involves applying a diversity factor. The NEC permits the use of diversity factors to account for the fact that not all equipment will operate at peak load simultaneously. The diversity factor varies based on the total load. Firstly, for the first 10 kVA of load, use a diversity factor of 1.0. This means the load is considered at its full value for this portion. Secondly, for the next 10 to 25 kVA of load, apply a diversity factor of 0.9. Thirdly, for any load exceeding 25 kVA, a diversity factor of 0.8 is used. These factors recognize that as the total load increases, the likelihood of all devices operating at maximum capacity at the same time decreases. The third step is to calculate the branch circuit load, multiply the running load by the appropriate diversity factor to determine the branch circuit load. This adjusted load figure is used to select the appropriate branch circuit size. The fourth step involves selecting the branch circuit size. Select a branch circuit size that is rated for the calculated load. It's important to choose a circuit that can safely handle the anticipated load, taking into consideration any applicable safety margins required by the NEC or local electrical codes. Here is an example. Consider a rack containing the following equipment. Firstly, 5 servers with nameplate ratings of 5 amps each. Secondly, 2 routers with nameplate ratings of 3 amps each. Thirdly, 3 monitors with nameplate ratings of 2 amps each. To calculate the total nameplate rating, you would add up the ratings of all the devices. This would be 5 amps times 5, plus 3 amps times 2, plus 2 amps times 3, which equals 25 amps. Now, let's consider the running load. Assume each piece of equipment typically draws 80% of its nameplate rating during operation. For the servers, this would be 5 amps times 0.8 times 5, equaling 20 amps. For the routers, it would be 3 amps times 0.8 times 2, which is 4.8 amps. And for the monitors, it's 2 amps times 0.8 times 3, which also equals 4.8 amps. The total running load is the sum of these individual loads, which is 20 amps plus 4.8 amps plus 4.8 amps, totaling 29.6 amps. Next, apply the diversity factor. Since the total load is less than 25 kVA, a diversity factor of 1.0 is used. This simplifies the calculation, as the branch circuit load is simply the running load multiplied by 1.0. Therefore, the branch circuit load is 29.6 amps times 1.0, equaling 29.6 amps. Finally, select a branch circuit size. Choose a branch circuit size rated for 30 amps or higher to accommodate the 29.6 amps calculated load. In this example, the branch circuit size is determined by the actual running load of 29.6 amps, which is greater than the sum of the nameplate ratings 25 amps. This highlights the importance of considering both nameplate ratings and actual running loads, along with any applicable diversity factors, to ensure accurate and safe branch circuit sizing for IT equipment. Ignoring the running load and diversity factors could lead to overestimating the required circuit size. Overestimation results in unnecessary costs and inefficient use of electrical infrastructure. The running load is the actual amperage drawn by the device under normal operating conditions. Nameplate ratings represent the maximum possible draw, which might only occur during startup or under unusual circumstances. Diversity factors account for the statistical unlikelihood of all devices in a rack operating at their maximum load simultaneously. These factors are based on empirical data and industry standards and are incorporated into the NEC to provide a balanced approach to circuit sizing. By following the NEC guidelines and considering the running load and diversity factors, it's possible to determine the appropriate branch circuit size for rack-mounted IT equipment. Accurate circuit sizing ensures electrical safety, optimizes power distribution, and reduces energy costs in data centers and other IT environments. The NEC provides tables and guidelines that offer specific direction on how to apply diversity factors for various types of equipment. For example, NEC Table 220.87 provides guidance on demand factors for feeders and services. While this table doesn't directly address rack-mounted IT equipment, the principles are similar. The goal is to assess the likely maximum demand based on the operational characteristics of the connected devices. Furthermore, it's essential to ensure that all electrical work complies with local electrical codes and regulations. These codes might have additional requirements or restrictions that must be considered when sizing branch circuits. Consulting with a qualified electrician or electrical engineer is recommended to ensure compliance and safety. Understanding and applying the NEC guidelines for calculating branch circuit size for IT equipment is crucial for electrical engineers, data center managers, and IT professionals. Accurate circuit sizing not only prevents electrical hazards but also ensures efficient power distribution and reduces energy consumption, leading to cost savings and environmental benefits. By considering the running load, applying appropriate diversity factors, and adhering to local electrical codes, it's possible to design and maintain a safe and efficient electrical system for IT infrastructure. Failure to accurately size branch circuits can lead to several problems. Firstly, overheating of conductors, which can damage insulation and increase the risk of electrical fires. Secondly, nuisance tripping of circuit breakers, which can interrupt operations and cause data loss. Thirdly, premature failure of electrical components, which can result in costly repairs and downtime. In addition to safety and reliability, accurate circuit sizing also contributes to energy efficiency. Oversized circuits waste energy and increase electricity costs. By sizing circuits appropriately, it's possible to minimize energy losses and reduce the overall carbon footprint of IT operations. Moreover, accurate circuit sizing ensures that the electrical system operates within its design parameters, extending the lifespan of electrical equipment and reducing the need for frequent replacement. In summary, calculating the branch circuit size for rack-mounted IT equipment requires a comprehensive approach that considers the running load, diversity factors, and applicable electrical codes. By following the NEC guidelines and consulting with qualified professionals, it's possible to design and maintain a safe, reliable, and energy-efficient electrical system for IT infrastructure. It's also important to consider future growth when sizing branch circuits. If the IT infrastructure is expected to expand in the future, it's advisable to allocate additional capacity to accommodate the anticipated increase in load. This prevents the need for costly upgrades and minimizes the risk of overloading the electrical system. One approach to planning for future growth is to use a load management system. Load management systems monitor and control the power consumption of individual devices, allowing for more efficient use of available capacity. These systems can also provide alerts when loads approach critical levels, enabling proactive management of electrical resources. Another important consideration is the type of power distribution system used in the data center or IT environment. Different power distribution systems have different characteristics and requirements, which can affect the sizing of branch circuits. For example, a three-phase power distribution system is more efficient than a single-phase system and can support higher loads with smaller conductors. Additionally, the use of power distribution units or PDU can simplify the management and monitoring of power distribution within the rack. PDU provide multiple outlets and often include features such as remote monitoring and control, which can enhance the reliability and efficiency of the electrical system. It's also important to consider the environmental conditions in a data center or IT environment. High temperatures and humidity can affect the performance of electrical equipment and reduce its lifespan. Therefore, it's essential to ensure that the environment is properly cooled and ventilated to maintain optimal operating conditions. Regular maintenance and inspection of electrical equipment are also crucial for ensuring safety and reliability. This includes inspecting conductors, connections, and circuit breakers for signs of damage or wear and tear. Promptly addressing any issues can prevent more serious problems from developing and extend the lifespan of electrical equipment. In conclusion, calculating the branch circuit size for rack-mounted IT equipment is a complex process that requires careful consideration of multiple factors. By following the NEC guidelines, considering the running load, applying appropriate diversity factors, and planning for future growth, it's possible to design and maintain a safe, reliable, and energy-efficient electrical system for IT infrastructure. Regular maintenance and inspection, along with adherence to local electrical codes, are essential for ensuring the long-term performance and safety of the electrical system. Finally, remember that the information provided is for educational purposes only and should not be considered a substitute for professional electrical engineering advice. Always consult with a qualified electrician or electrical engineer before undertaking any electrical work. They can assess the specific requirements of the IT environment and ensure that all work complies with applicable codes and regulations. Moreover, it is important to consider the impact of power quality on IT equipment. Power quality refers to the stability and reliability of the electrical power supply. Poor power quality, such as voltage sags, surges, and harmonics, can damage IT equipment and disrupt operations. Therefore, it's essential to implement measures to mitigate power quality issues such as installing surge suppressors, voltage regulators, and harmonic filters. Uninterruptible power supplies or UPS are also crucial for protecting IT equipment from power outages and voltage fluctuations. UPS provide backup power in the event of a power failure, allowing IT systems to continue operating until the power is restored or the systems can be safely shut down. The size and type of UPS should be carefully selected based on the power requirements of the IT equipment and the desired level of redundancy. Another important consideration is grounding and bonding. Proper grounding and bonding are essential for preventing electrical shock hazards and minimizing electromagnetic interference, or EMI. Grounding provides a low impedance path for fault currents to return to the source, while bonding ensures that all metal parts of the electrical system are at the same potential. The NEC provides specific requirements for grounding and bonding, which must be followed to ensure safety and compliance. Additionally, it's important to consider the use of energy-efficient IT equipment. Energy-efficient servers, routers, and monitors consume less power and generate less heat, reducing the overall load on the electrical system. This can result in significant cost savings and environmental benefits. Furthermore, the use of energy-efficient equipment can reduce the need for cooling, which can further reduce energy consumption. In summary, calculating the branch circuit size for rack-mounted IT equipment is just one aspect of designing and maintaining a safe and efficient electrical system for IT infrastructure. It's also essential to consider power quality, grounding and bonding, and the use of energy-efficient equipment. By taking a holistic approach to electrical system design, it's possible to create a reliable and sustainable IT environment that minimizes energy consumption and reduces the risk of electrical hazards. Remember to consult with qualified professionals and adhere to all applicable codes and regulations to ensure safety and compliance. Finally, continuous monitoring and management of the electrical system are crucial for identifying and addressing potential issues before they become problems. This includes monitoring power consumption, voltage levels, and temperature, as well as regularly inspecting electrical equipment and performing preventive maintenance. By proactively managing the electrical system, it's possible to ensure its long-term performance and reliability.